Welcome back. In the past two lectures, we talked about processes and threads as the two main abstractions for execution. A process encapsulating all of the running state of an instance of a running program, and threads that encapsulate the execution context that contain separate local variables and CPU registers. So today we're going to start to build on this to look at how do we deal with multi-core machines and how do we scale to many cores. This is interesting because today this is a major issue, right? We can easily buy CPUs with 16 or 32 cores off the shelf, even on high-end desktops that consumers might own. So how do we make use of these resources is a really important problem that all programmers are going to face. So we have here, to illustrate the problem, two simple functions, add and subtract. Add increments a global variable total, and subtract is decrementing that same variable. So we might think that we could run these things in parallel, but this is actually not the case. The first thing is that when you compile this code down, you'll see that we're looking here at the MIPS assembly, roughly, that the compiler would generate, that we can have a load instruction, an add, and a store instruction, and here a load, a subtract, and a store. So the two operations are not atomic. You don't instantaneously update total. This means that if we run these two functions in parallel, we could get different interleavings of these instructions executed at the same time on different cores. So let's look a little bit at three examples of how this could happen for this particular set of functions. So here, in Schedule 1, we show that the first thread executes entirely, and then the second thread executes. Here, these interleavings work. The first one adds 1, the second one is going to subtract 1. So the net result is that we're going to result with a net of 0. But there's obviously many other schedules that are possible. We can look at a second schedule where we load on both threads and then we do the operations. And these operations are occurring in the CPU registers, so they're not affecting each other. They're in separate threads with their own CPU registers. And then the stores occur. Here, what's the result going to be? Well, the store of thread 1 is overridden by the store on thread 2. So thread 1, it's almost as if it had never run. And the result is going to be a -1. Similarly, we could imagine all kinds of other schedules. Here's one more, where the opposite's happening. The store on thread 1 has overridden the store on thread 2. And we end up with a result of 1. The problem is that data races can occur if we don't have some kind of proper synchronization. And broadly speaking, there are two options for you. The first is going to be atomic instructions, where we use a processor feature to ensure that that operation happens instantaneously from the perspective of other threads. And two, we could use locks to prevent the concurrent execution of a particular code path between two threads. But first, I want to dive in a little more background into why this is such an issue and see how this even gets worse. So here, I have an example, program A, that I've created, and it has several functions that are going to run in parallel. Main spawns a bunch of threads, and it's going to run P1 and P2 at the same time. So what could happen if both of these threads run? Well, let's look quickly at what these things are doing. P1, it sets flag 1 to 1, and then if flag 2 is 0, then we're going to run critical section 1. And P2 is going to set flag 2, and if flag 1 is 0, it's going to run critical section 2. Is it possible that we can run both critical sections? So you can think through quickly the different options here, and you could pause the video for a second if you'd like. P1 could run first and set flag 1, and then it checks and it sees flag 2 is 0, so critical section will run. 1 will run. P2 then runs, and it sets flag 2 to 1, but flag 1 has already been set, so the second section doesn't run. Okay, we could have another interleaving where we run P2 first, and we'll see only one of them will run. What if we ran them at the same time? Well, if we ran them at the same time, we think that flag 1 and 2 are both being set to 1 first, and then they're both checking whether they're 0, and neither will run. Is this right? Or is it possible that we could still run both? Let's look at one more example here. Here, again, let's assume that we're running P1 and P2 at the same time. P1 sets data to 2000 and marks the ready bit, and P2 waits while the system's not ready, and then it tries to use the data. Could we ever call use with data being 0? If you think about this logically, it seems like this shouldn't ever happen. Right? You're assuming that when the ready bit is set, data has already been set. Let's look at one more example. Finally, we have 3 functions here, P1, 2, and 3, where P1 sets A to 1, P2 checks if A is equal to 1, then it sets B equal to 1, and then P3 sets B equals to 1, and then tries to use the value of A. Could we ever call this with a 0? If you think through this logically, it seems that B1 must be set, and a B1 can only be set if A1 was set. And A1's only set after P1 runs. So it seems like we shouldn't be able to see this. But the reality is that we don't know. It is actually possible that you get all of those results that we asked, but it depends on a lot of factors. It depends on what kind of machine you're using. It depends on what the system provides. If the system provides sequential consistency, then the answer to all of these questions is no. And we'll see what this really means in a second and define this. But most hardware doesn't provide sequential consistency. So sequential consistency is an important idea to understand for understanding how do we understand what programs do when it comes to executing on multi-core machines. Sequential consistency just says that the result of the execution is as if all operations were executed in some sequential order, and the operations of each processor occurred in the order specified by the program. So what it means is that it means almost exactly what you assume your program is doing, that all of the operations occur in the order that you wrote them in the program, and that all writes are atomic from the perspective of other processors. It turns out that most hardware doesn't provide the first guarantee. It doesn't ensure that things are in program order. And 2, some hardware, some embedded processors specifically, don't ensure write atomicity. Without sequential consistency, when we have multiple CPUs, we can see operations occur that wouldn't be possible with any interleaving of threads on a single CPU. So why is it that hardware doesn't support sequential consistency? This seems insane. How can I reason about my programs? The reason is that sequential consistency really makes it hard to do lots and lots of optimizations, both for the hardware and the compiler. Okay. Sequential consistency prevents hardware optimizations. It complicates how write buffers are done in the hardware. Right? You might see some of the flags being read before previous flags were written because of the buffering that's occurring in the processor. the processor wouldn't be able to reorder overlapping write operations. Imagine writes to two different memory modules that want to be done concurrently, or coalescing writes to the same cache line. Third, it complicates a lot of non-blocking reads, either speculatively prefetching or even code prefetching of data. And lastly, it makes cache coherence more expensive. It's going to complicate the protocol that's required to synchronize the reads and writes to memory between all of the cores in a processor. Sequential consistency also prevents the compiler from its optimizations. You can't move code around to optimize the code layout. You can't cache values in a register. Imagine that you read a certain value many times. The compiler might read that value into a register, operate on it, and store it a single time rather than reading and storing it multiple times. Often you'll have expressions that are reused in your code, and the compiler will cache that expression, avoiding the reads of the underlying variables. This also affects how we reorder loops, and it affects software pipelining of instructions in a loop, because these are all sort of variations of code motion problems. So we need to understand a little bit about how hardware deals with consistency from a software perspective, and then start thinking about the kinds of instructions and building blocks we have to solve these concurrency problems. So x86 and many other processors usually support multiple consistency models. They have a set of memory type range registers that allow you to change the consistency model for various uses. Hardware, device memory that we'll see when we start talking about devices and I/O later in the course might specify a particular consistency model so that it understands when data is flushed. And you also have some page attributes. When we talk about memory management, we'll come back and see how these are set and what this really means, that also allow you to control the consistency model. This isn't too important, but the important thing is to understand that there's different consistency models for memory. And the choices here are pretty comprehensive for most architectures. We have a write-back caching model. This is the default. It means that when you do reads and writes to memory, they will be stored in cache, and eventually they'll be flushed back to memory. A write-through caching model, where all writes will go straight through into memory. An uncacheable model, this is often used for devices where we do not want to do any caching whatsoever, and we want every load and store in the instruction set to map to an actual read or write operation. When we talk about device memory, we'll see again about this. And write combining. This is a weak consistency model with no caching that's often used for graphics data, where we want to send data through to memory. Some instructions also have weaker consistency models than others. So there are a couple interesting examples. One is the string copy instruction. So in x86, string copy and mem copy and mem move can be implemented as a single instruction using the rep prefix on a move instruction that moves between two memory addresses. These instructions actually relax the consistency for all of the data inside of the move until the move instruction has completed. You're not guaranteed to see any order of operations until that move, the mem copy or string copy operation, has completed. So let's look at the most common consistency model, the write-back consistency model. This is what most programs use when they're running on a modern desktop. A few of the very old x86s, from 486s and the early Pentiums, they almost had sequential consistency. Only one rule is broken, which is that reads can finish before an earlier write to a different location. So which of the three programs that we listed, A, B, and C, could be affected? It's just program A. The other two behave as a sequentially consistent program on these processors. Newer processors, though, make this more complicated. They also let the CPUs read their own writes early. This is known as store-to-load forwarding that allows the processor to accelerate a load of a known location by forwarding the store that was done previously. So here we can look at an example, and if we run P1 and P2 in parallel, we can see that the result is these can both return 2. P1, so here P1 executes in parallel with P2. P1 sets flag 1 to 1. The processor will forward the value of flag 1 to F, and then it'll read flag 2. It's possible that these could get reordered, and we'll have F being 1 and G being 0 for P1 at the same time that P2 runs, where flag 2 is set to 1, the store-to-load forwarding forwards flag 2, and flag 1 is read as a 0. And both functions simultaneously return the value 2. This doesn't seem like it should make sense, but this is possible because of these reorderings that are allowed. One of the nice things is that x86 is one of the strictest memory models that we have. The write-back consistency model in x86 can cause these anomalies to occur, but it is stricter than a lot of other processors. For example, the MIPS processor that we're using for OS 161 has a more relaxed consistency model. x86, like most processors, provides a set of instructions for atomicity. In x86, this is provided through prefixes. These are instructions that modify the following instruction. Any memory operation that has the lock prefix will essentially behave as an atomic instruction. In older machines, this might have been implemented by locking the bus for some amount of time while the operation completed. On modern ones, it can be avoided by exclusively caching the data on the local processor, modifying the memory, and then releasing the memory to the machine. All lock instructions are going to be totally ordered, so they behave sequentially consistent. Other memory instructions are not going to be allowed to be reordered with locked instructions in the x86 architecture. And x86 also provides a few additional instructions that don't need the lock prefix: exchange and compare and exchange, that both allow you to exchange a value between a register and memory, or to compare a value and then conditionally exchange the value between a register and memory. In addition, even without these operations, you can also block the reordering of reads and writes, or reads and writes, through fence instructions. These instructions block reordering operations before and after the fence to ensure that the writes that you expect to be visible to the rest of the program are. Typically, you're not going to write directly these instructions. You'll use the compiler's help to provide you with that functionality and to help automatically insert these instructions where needed. Generally speaking, when you're debugging your program, you should assume sequential consistency. In fact, compilers also make this assumption. They assume that without any data races in your program, that the code will behave sequentially consistent. For low-level code where you're having synchronization, you're going to need to use atomics and barriers correctly in the source code to ensure that the compiler understands when there is communication between threads and where there might be non-sequentially consistent behavior if the compiler does a reordering operation. For most code, we can avoid this by just depending on the memory model. As we'll see a little later, that if we obey some simple rules, the system will behave indistinguishable from sequential consistency. Let's for now assume that we have sequential consistency and look at a simple producer-consumer example to see ways that we deal with. So here we have a producer-consumer example where we have a queue of items in a ring buffer. The buffer variable is size buffer underscore size. And we have two pointers in and out that point to the front and tail of this queue. The producer creates items, and while the buffer is full, it doesn't do anything. And when the buffer has space, it'll insert the item into the buffer and then increment the in value. And the consumer, similarly, waits while the number of items in the buffer are 0. It's going to do nothing. And when there is items in the buffer, it's going to read from the buffer. And it's going to then increment the out and decrement the count, and then consume the item. So what can go wrong? Think back to our first examples that we had. Anything here that's shared basically can go wrong. The counts might be read and written overlapping such that the counts don't get incremented and decremented correctly. The compiler has no awareness about what's happening, so it might actually cache the count value and sit there in the while loop, never actually making forward progress. So you call while count, the compiler caches count in a register and reads from the register 0, and it assumes that the while loop is there stuck forever. All of these things can happen because of all the optimizations that are possible in the hardware and software that we talked about. So we need some solution to communicate correctly our intent to the language and to the hardware underneath. So what we need is a solution to create a critical section, a section of code where the count increments and decrements and the other operations that modify shared memory between these two threads, between the producer and consumer, will not run concurrently, that will protect that concurrent execution. We have three main desired properties. The first, mutual exclusion, which is that we don't want one thread to enter the critical section at a time. Two, that we want to guarantee progress. We want to ensure that if there are no threads currently in the critical section, eventually one will get in. And three, we want a bounded waiting time. We want to ensure that if multiple threads are waiting to get in, the number of times other threads get in before any given thread gets in is bounded. Essentially, this is some form of fairness between all of the possible threads that might try to enter the critical section. Let's look at one of the earliest solutions to critical sections. For those of you taking the concurrency course in your 4th year, you're going to see this in more detail with other variations that avoid some of the limitations in the example I'm showing now. Here, I'm going to assume still sequential consistency, that we've told the compiler to make things sequentially consistent in terms of what the processor sees. And I'm going to assume that I have two threads, T0 and T1. And we have two global variables, not turn and once. And all we have to do is execute through this loop where we have the critical section code that is modifying shared data structures and the remainder section that is modifying data that is not shared. And the way that the critical section works is that each thread sets its own wants flag. It sets that it wants to enter the critical section and then says that it's not its own turn. And while the other thread wants the critical section and it's not our own turn because we set it above, then we'll wait for the other thread to complete. When the other thread completes, we'll be able to enter the critical section. And once we're done, we set the once flag to false. This would, if you think about the other thread's perspective, the other thread would see that we've released that flag and that it was not their turn, and they'll be able to make forward progress. So does this solution work? So the mutual exclusion both threads cannot be in the critical section. If both threads were to be in the critical section, it means that the both once flags would be set to true. And soturn would have to have blocked one thread from the critical section. So mutual exclusions works. The second is, are we making progress? If one thread is not in the critical section, then I can't block the other thread, meaning that if one thread's 1 minus I is the alternating thread's flag is false, then TI won't loop. And lastly, do we have a bounded waiting? And it's a similar argument to progress here. If TI, if the front thread wants a lock, the alternating thread tries to enter, and T1 minus I will be set, and not turn will equal 1 minus I, allowing TI to proceed. This is a really simplified version of Peterson's solution for just two processors, and this will get more complicated depending what assumptions we're going to break and how many cores. But this was really used on machines where atomic instructions weren't present. So we can do something much simpler today on most modern processors. You may actually still see Peterson's solution on embedded chips that do not have atomic instructions. But today we can assume that we have various kinds of locks. Generalizing Peterson's to many processors becomes fairly expensive. And so we'd like a nice set of abstractions that are going to provide us with synchronization. And the most basic one is what we call a mutex lock, a mutual exclusion lock, often referred to just as a lock. All global data should be protected by a mutex. You never want to access shared data between two threads without using a mutex or some other kind of lock primitive to protect that state. The exception might be during initialization, where none of the other threads would have been exposed to that state. And you as the programmer are responsible for doing this correctly. If you use mutexes properly, then the behavior of your program should be indistinguishable from sequential consistency. Remember that the contract most compilers give you in C, Java, Go, and other languages is that assuming that there are no data races, then the program will behave as equivalent to a sequentially consistent execution of the program. So one of the interesting things to see is that most compilers and languages are aware of the lock primitives and the atomic instructions that you're inserting to ensure that they don't make optimizations that could break sequential consistency. Also, operating system kernels themselves need synchronization. It's a little bit different. While you can use mutexes in the kernel, we'll see an alternative to mutexes that are often used for really short critical sections. But these aren't used in user space, even though they function identically, because of the assumptions of the environment. As you'll be using pthreads in your assignment 1, we're going to use the same pthreads locking primitives throughout this lecture. So here we have the basic mutex operations that can be done. The first is to initialize a mutex to create a lock. to destroy the lock, and then the main operations, lock, which acquires the mutex, only one thread will be able to acquire that mutex at a time, and unlock, that's going to release the mutex, allowing other threads to proceed, and finally, a try-lock that allows you to attempt to acquire the mutex. If you're successful, it returns 0, otherwise it returns -1, and it sets the error no global variable to eBusy, telling you that someone else already has the lock. So let's go back to the producer-consumer example and see how we change our code to correctly use mutex locks. Here, we have the producer. We produce an item. Remember that this item is being produced and it's being stored in a local variable, the pointer to this item. So we want to do this outside of the critical section. But if we want to check how many items are in the critical section, we'll have to while loop checking count while holding the mutex lock. So we acquire the mutex lock. We call PThread Mutex lock. We acquire it. Then we can check whether or not the buffer is full. If the buffer is full, we're going to unlock the lock, yield, allowing other threads to proceed, and then reacquire the lock. So why are we unlocking and relocking here? The reason is we want to make sure that if the buffer is full, the only way to make forward progress is if the consumer runs and consumes an item. So we need to unlock the lock and then yield, allowing other threads to run, and then we can reacquire the lock to recheck the count. Now when we've exited the loop, we're still holding the lock and adding the produced item into the buffer, incrementing the buffer, and incrementing the number of total items is all done while holding the lock. And finally, we'll release the lock before we produce the next item. The consumer, similarly, is modified in a similar way, where we grab the lock, we check whether or not the buffer is empty, and if it is, we're going to unlock and yield, letting the producer to run, and then reacquiring the lock. The important thing here is that all of the modifications and reads and writes, specifically to shared variables, count, out, and the buffer itself, are done while holding the lock. Consuming and producing the item can be done outside of the lock. Assuming that that takes some time, then this critical section will execute very quickly. It'll just be a few assembly instructions that checks whether or not there's an item in the queue, reads the item, and then increments and decrements the numbers out and count. So there's one problem with this code that I'm showing here, which is that here we're always unlocking the lock and then yielding, hoping that the producer runs, and then trying to reacquire the lock. This isn't really efficient, and this is a really common design pattern where we're communicating between many threads. So if you're wondering where you might be using this, you can think about Go channels. Remember last lecture, I had the example of diving into how the Go language works and how it deals with threads, and I mentioned the Go channel primitive. And the Go channel primitive is basically just a queue that allows us to produce and consume items. And when you're reading and writing from the queue, it effectively looks like a single execution of the producer and consumer code you see here. The problem being that if we're trying to unlock and wait and yield and then let the other thread run, well, maybe we're going to yield and other threads in your system are going to run that are not the producer. And this will be really inefficient. We might yield many times, reacquiring the lock, running, and the producer still hasn't run. So what we need is we need a way to tell the operating system that we want a specific thread to run. We want the operating system to know what thread we depend on. And this introduces the idea of condition variables. Condition variables allow us to signal to the operating system scheduler that a specific thread, we're waiting on that thread, or that we want that thread to wake up, and that some state that that thread needs has been modified. Condition variables work in conjunction with the mutexes, and there's 4 basic functions. The first being condition init, that's going to create the condition variable and initialize it. The second being condition wait, and condition wait is interesting because you're going to pass in the condition variable and the mutex. And what it's going to do is it's going to unlock the mutex atomically while going to sleep, waiting on the condition variable. And then when another thread wants to wake you up, it's going to call conditional signal or broadcast to wake up one or all threads in the system that are waiting on that specific condition variable. And then that wait, those threads that are currently inside of condition wait, will be rewoken up and they'll reacquire the mutex. So if multiple threads are woken up from the broadcast, one of the threads will acquire the mutex and proceed, and when it releases the mutex, other threads can acquire the mutex and proceed. So let's put all of this together and improve the consumer-producer example to see how we can use condition variables. And here, we're going to need 2 condition variables. One that is used to signal on the non-empty condition, and another that's used to signal on the non-full condition. So the code looks a lot like last time, but we've replaced the unlock and relock and the thread yield with a condition wait. So when the buffer's full, we wait on the non-full condition to see when the buffer is no longer full. And we're going to release automatically the mutex and reacquire it when we wake up. We'll then produce a new item, adding the new item to the buffer, and signal on the non-empty condition. And if we look at the parallel, the consumer code, we'll see that in the consumer, if the buffer is empty, it's going to wait on the non-empty condition. So when we produce an item, we signal the non-empty condition waking up the consumer. And over here, similarly, once we've consumed an item, we always signal the non-full condition. Obviously, if you've consumed an item, there should be at least one space available, so we can always signal the non-full condition, allowing the producer to run once. So there are a few key things to remember with condition variables. While there are 2 variations of condition variables, the condition variables that are used by virtually all modern systems requires you to always tree check the condition on a wake up. So here you see that you use a while loop still, checking that count is equal to 0 or that count is equal to a full buffer before calling condition wait. It's not an if. The reason is there's a few possible things that can occur. One is we might get woken up spuriously. For various reasons, there might be other things that happen in the system that cause us to get woken up, even though the buffer is not ready. And 2 is if you have multiple consumers or producers, then you have to also think about the case when these 2 are racing to acquire items or produce items on the buffer. And the reason this is possible is that condition wait doesn't reacquire the mutex atomically with the wake up. So when condition wait wakes up, it's possible that another thread could enter, acquire the mutex before the condition wait reacquires the mutex for you. It then executes and consumes the item, and then there's no more items in the buffer. So this is an important thing to remember, is that while going to sleep for condition wait is atomic with releasing the mutex, this ensures that you never go to sleep without possibly being signaled. It is not the case that the wake-ups are atomic. Alternative designs to condition variables do fix this, but nobody actually uses those in production. So let's dive into a little bit why each of these things are the case. Why is it that condition wait releases the mutex and sleeps atomically? Well, if we try to do these things separately, what could happen? So here, I mutex unlock, and I have a wait that doesn't do the release of the mutex atomically. And then I try to reacquire the lock. What could go wrong? The simple thing that can go wrong here is that we unlock the mutex, and the consumer reacquires the lock. It consumes an item and then sends a signal before we actually were able to wait and go to sleep on the mutex. So we'll miss this signal here to the condition wait function. That means that the producer might sleep and never wake up if the consumer doesn't run again. So let's look at one more synchronization primitive, and that is semaphores. Semaphores allow you to initialize a count to n and then to use two functions, wait and signal, originally called p and v, that increment and decrement these counts. When you call semWait will return up into n times. After that, when the count has reached 0, it's going to sleep. So every time you call semWait, it decrements the count by 1, and once it reaches 0, further calls to semWait will sleep until someone else calls semSignal, incrementing the count above 1. And there's a nice case here where if we set n to 1, then we can use a semaphore as a mutex. So we can call semWait the same as a mutex lock, and we can call semSignal to unlock the lock, similar to mutex unlock. Semaphores are nice because they give some elegant solutions to certain kinds of problems. In fact, in the Linux kernel, semaphores are used primarily for certain kinds of sleeping locks. There's also a few other variations I cite here of read-write semaphores and other versions that have specialized applications. So let's go back to our producer-consumer example and see how we can write this with semaphores. I chose this example because this is a case where you can write this with semaphores very elegantly. You produce an item, you call semWait, and the semaphore is initialized, the full semaphore is initialized to 0, and the empty semaphore is initialized to n. So we can produce n items before we sleep on this semWait call, and we can signal n times, because we are blocked by the semWait, until the buffer is completely full. Similarly, the consumer can run waiting on the number of times that full has been signaled. And semSignal will be sending signals to the empty to tell the producer that it is able to produce new items. One of the nice things here is that the semSignals and waits can run multiple times before the other thread occurs. They don't actually have to run concurrently. So in this case, empty was set to n. We can iterate n times through this producer function before we fill up the buffer and semWait is called, sleeping on a buffer on the empty semaphore. And then that'll actually cause the consumer to run, because the consumer would have been blocked on semWait, and it could run up to n times before it's emptied the buffer. So you could have execution schedules here that don't necessarily have to bounce back and forth between these two threads. It also, as you can see, this produced the simplest code possible for this function. This is much simpler than the lock case, and you don't have to worry about continually checking a condition, because the condition is implemented by the semaphore itself. Knowing how many items are in the queue or how many spots are free are determined by the semaphores themselves. So we don't need to while on count, and we've actually eliminated the count variable entirely. So today, we looked and introduced some of the basic problems in concurrency and 3 main solutions that are very common for people writing multi-threaded applications. Mutex locks, condition variables, and semaphores, which are three of the most common primitives that you'll use. Next time, we're going to pick this up to look at a few more things. Spin locks, which look a lot like mutexes, but are used typically in the operating system kernel. Different ways that these things can be implemented, and shared reader-writer locks that allow us to have concurrent reads while having exclusive writes to critical sections. We'll also get to see how we generally try to make programs faster and some ideas around that, and then look at some real-world examples of where these things come into play in modern-day systems.